Hello, my name is Jan-Malte Giannikos, and this is a short overview of the research I conducted on tree deformation prediction as part of the RIS 2022 program. Using robots to automate physically strenuous work in agriculture is a compelling objective. However, it usually requires the manipulation of crops, which are often complex and irregular structures. Trees are no exception to this rule, and yet, to create a closed-loop system that can harvest fruit or prune trees, we need to have a solid grasp of tree manipulation. The problem is commonly approached by dividing it into three sub-problems: creating a representation of the plant, modeling its physical properties, and finally, planning a policy. Our work targets the second step, aiming to predict how a tree deforms under external force by using graph neural networks. Since collecting a large data set from real trees was deemed too costly, we instead aimed to generate a synthetic data set in simulation. To do so, we first utilized the space colonization algorithm to generate tree topologies in the form of tree points connected through branch sections. We imported the generated tree topologies into the physics-based simulation environment ISAC-GYM. Branch sections were imported as rigid bodies that were connected through three-dimensional joints. Each one of those three-dimensional joints was assigned a stiffness based on the radius of the incoming branch segment. In cases where one branch segment split into multiple children, a separate joint was created for each child, allowing them to move semi-independently from one another. To simulate pushes, we applied a random force to a random tree node. With this method, we generated a primary dataset containing 25 trees with 8 nodes that were each subjected to 10,000 push interactions. An additional secondary dataset containing 24 10-node trees was constructed to test for generalizability. We found two ways of translating the graphs saved in our dataset into useful graphs for our graph neural network. The first aimed at predicting the positions of the tree nodes after the push directly, while the second aimed at predicting the orientations of each branch segment, reconstructing the positional data in a post-processing step. The formalism used when predicting positions had a node for every joint in the tree, saving its position and the orientation of the outgoing edge. When predicting orientations, we instead opted to create a node for every branch segment, saving its orientation, the position of its origin, and its length. We used a residual graph convolutional network with one-dimensional batch normalization and dropout after every layer. The number of network layers was chosen equal to the number of tree points in our training dataset. This allowed us to guarantee that the message passing between the most distant nodes was possible. However, this also meant that generalizability to more complex trees was limited, since we could no longer guarantee that message passing between each node was possible. The exact architecture of each model layer is depicted here. Notice that we introduced a residual skip connection from input to output and added a linear layer to the basic graph convolutional network layer at the heart of this architecture. In our tests, predicting positions generally outperformed predicting orientations. However, positional prediction has its own problems that become especially apparent when testing for generalizability. We reached the highest accuracy when the models were tested on tree topologies that had also been in the training dataset. When we instead tested separate tree topologies, we saw a moderate performance loss that was, however, still in the realm of the acceptable. Finally, when testing models trained on 8-node trees with a test set containing 10-node trees, a further drop in performance occurs. When looking at examples for tree deformations, we can see some of the issues that each prediction approach brings with it. Predicting orientations suffers from an error propagation issue. Since we reconstruct the tree positions from the root node up, errors in the early branch segments add up, leading to higher errors in the tips of the tree. When predicting positions, especially when testing a model trained on 8-node trees on 10-node trees, we see branch warping effects. Since the distance between two joints is not explicitly encoded anywhere in the model has the ability to shorten branch segments. It can also predict that two joints attached to the same parent segment are in different positions, leading to branch splitting effects. Since these errors fundamentally impact tree structure in a seemingly random manner, it might be advisable to use orientational prediction when generalizing to more complex trees. Our future work will be aimed at introducing our models to real tree data, as well as the use of more flexible graph neural network models that allow us to overcome the message passing limitations graph convolutional networks bring with them. Finally, I want to thank Rachel Burson and John Dolan and all others involved in the RISC program for making this project possible. My sincerest thanks also go to the DAAD for sponsoring this research, as well as Oliver Cromer, Munyoung Lee, and all other members of the IAM Lab for supporting me on my research journey. Thank you very much.